Hi, this video is about real number sets. I'm going to give you a little introduction as to how to classify real numbers into their more specific sets, and I'm also going to give you some examples at the end to help you out. So how do I classify real numbers? Well, first of all, let's start with some abbreviations that we use just to make it a little easier to write. The letter R stands for real numbers. So let's start off with, what is a real number? Well, a real number is any number that you use in everyday life. So any number that you've used up through Algebra 2 would be considered a real number. And you can kind of think of them as points that you can find on a number line. You've never used anything other than a real number in any math class up to Algebra 2. We will be using complex numbers a little later. But for our purposes right now, we're only going to be dealing with real numbers. Okay, so once a number is real, it can be broken down into two sets, one of two sets. The first is rational. That's denoted by the letter Q. And the second is irrational, denoted by the letter I. Now, the reason that the rational numbers are denoted by the letter Q is R stands for real, so you couldn't use R again. So another letter was chosen, and it was Q. The technical definitions of the two: rational numbers are numbers that can be expressed as the quotient of two integers, and irrational numbers are numbers that can't be expressed as the quotient of two integers. Well, that's kind of hard to remember sometimes, so the easy way to remember it is rational numbers are decimals that terminate or repeat. A terminating decimal ends, a repeating decimal goes on forever and has a pattern. Irrational numbers don't terminate or repeat. They go on forever with no pattern. So what are some examples? Let's start with 1.3. That terminates, so that's a rational number. 2/5 is an example of a rational number. Translate that to a decimal, that's 0.4. 0.4 is a terminating decimal. .8 repeating. That line shows that it's a repeating decimal. Since it repeats, it's rational. 9. -11. Those are all examples of rational numbers. Well, how about irrational numbers? Well, the most famous one is pi. Pi goes on forever and has no pattern. Another one, square root of 2. Now the decimal for the square root of 2 is 1.4142135, and it keeps on going forever. And there's no pattern to it, so that's an irrational number. I could just make one up. 3.76241 ... The ... means that it goes on forever. It doesn't have a pattern to it, so it's irrational. So if it's a real number, it can be broken down into one of two sets, rational or irrational. It has to be one or the other. So if it's rational, it can be one of these three. It can be 2 or 3, or it can be none. It can be any or all. Integers. Integers are denoted by the letter Z. It's not I because irrational has the I already. They're numbers that don't have a decimal component to them. So if it has a decimal, it's not an integer. So any of these numbers are integers. And it goes on forever in both directions. So it goes negative and positive, and it includes 0. Whole numbers are denoted by the letter W, and they are positive integers including 0. So everything from 0 up is a whole number, denoted by W. Natural numbers are very similar to whole numbers, only they don't include 0. So these are the counting numbers, you could think of it that way. But whole and natural are very close, only natural numbers do not include 0. Okay, so that's how it is in words. What does it look like as a picture? All right, there's a picture. This whole box represents all the real numbers. They can be broken down into rational or irrational. If they're irrational, they can be none of these others. If it's rational, it can be an integer, it could be a whole number, it could be a natural number. Notice how the boxes get smaller as the sets get more specific. There's some examples of each. Some of those I've given you already. All right, let's do a few examples. Okay, let's start off with 3. 3 is a real number. It's also rational because it's a terminating decimal. 3.000, but you just don't write the zero, so it terminates. It's just 3. Real, rational. It is an integer. It does not have a decimal component. It is whole, and it's also natural. So RQZWN. Numbers cannot have a Q and an I because it's either rational or irrational. It can't be both. All right, example number 2, 1.7. Well, that's real. And it's also rational because it's a terminating decimal. It is not an integer because it has a decimal. And if it's not an integer, it can't be whole or natural. So I'm just going to stop with R and Q, real and rational. Next one, let's try negative 15. Negative 15 is real. It's also rational. It's an integer because there's no decimal. But it's not whole or natural because it's negative. So it's real, rational, and integer. Let's try square root of 3. Now, in order to figure out what the square root of 3 is, you have to type it into the calculator. And you get 1.732050808. And it keeps going on forever. There is no pattern to that. So the square root of 3 is irrational. So it's real and it's irrational. Once it's irrational, I stop. It can't be anything else. And last, let's try 0. 0 is real. It's rational. It's an integer. It's a whole number, but it is not natural. So real, rational, integer, and whole. That's a tricky one because it does not include n. And that's it. That is real number sets.